Hello, welcome to the numerical ship and offshore hydrodynamics. Today is the lecture 57. Now, today we are again going to discuss the ship hydroelasticity using semi-analytic method. So, today we are going to discuss about how we can solve that ODE and find out the structural deflection, that amplitude of the structural deflection. Okay, and this is the keyword that you have to use to get this lecture. Okay. Now, here actually we stopped in the last class. Now, we discussed about how we can get this FNT, right. We discussed how we can get this FNT, right, and but then we really did not discuss about the second part. Now, this is as you know that this is kind of Dirac delta function. Now, what is we are assuming that if the exciting force actually it is kind of hammering that each cross section, maybe there is not much mathematical base to approximate this, but here the physically what we assume that suppose we have the shape and then wave, it is hitting like an impact force in all sections. Okay. So, that is how actually we thought of, right, and then here and this is the way I can get the suppose I get the frequency domain exciting force. Of course, that is actually it is required when you write this impulse response functions with method. Always you record the data from the frequency domain. Now, this FNW is the frequency domain exciting force. So, when you have this, you can get this FNT using the Fourier transformation, right. Now, assuming that you have this, you have the Fourier transformation, you get this FNT and you write this expression 2.12 to write the exciting force. So, then if you integrate along the length L, and then this frequency the exciting force is looking like 2.14. Now, this is the property of the Dirac delta function, right. So, if you integrate this Fnxc multiply the Wx, then if you replace this Fex as Fnt into Dirac delta function x minus x naught into dx, right. So, let me write it a little bit bigger way. It is, if you write it as Fnt into Dirac delta x minus x naught into dx, then definitely you will get this quantity. So, it is the physical, it is that each sections actually you can as if it is coming as a hammer. I mean, as I said, there is not much mathematical backup for this particular thinking, but somehow this works. Okay. Now, you substitute this 2.14 into the original the equation where you have the radiation force and the diffraction force. So, if you substitute there, so this is how actually you can write the total the right hand side of the equation, right, that right hand side of the that beam equation. So, now as you know that we are going to use the property of the orthogonal property of Wnx and Wmx, and we use that and we ignore the cross coupling term, right. So, therefore, when m not equal to n, it is 0, then when m equal to n, we have now if you make it orthonormal, then this becomes equals to 1, otherwise you have the some values, right. So, this is well known to everybody. So, therefore, if you do this and use this orthogonal property, then finally actually you can arrive at 2.16, then actually this all the spatial coordinate actually you can remove, right. So, when this n not equal to m, so let us take the it is up to you how you are writing this Wnx and Wmx. If you write it in an orthogonal way, so then this when Wn and Wm integration, this is equal to 0 when n not equal to m, and then it is equals to some value k or 1, it depending on whether it is you are using orthonormal mode shape or orthogonal mode shape. Anyways, now this is the part of the structural, and I really know that you all know this very well, and we do not have much time to discuss all these things, very elementary, right. So, we can skip it, and but if you use this property, definitely you will get this equation 2.16. Now, here the idea is how I solve this differential equation 2.16. Now, numerically, there are lot of numerical methods are available, like you can use the Euler method, then Newmark beta method, and then so many methods. I mean, Adam Walton method, predictor character method, so many methods are there, right. Runge-Kutta method, but here we did not use any of these methods, where we are using some kind of semi-analytic technique using the Duhamel integral. Now, what is again Duhamel integral? We are not discussing here. You can just browse and you can uh, get the knowledge about the Duhamel integral. It is very well known. Now, how we use here, that is the question. Now, here if you apply this Duhamel integral, then your displacement actually looks like in this fashion. Now, as I said, first of all we have not much time to discuss how applying Duhamel integral we are getting it. So, we can ignore at this point, it is really not that necessary. Necessary is try to find out this q and t, that the value for the displacement, right. Anyway, or how to solve this equation 2.17. Now, here this 2.17 we actually solve in semi-analytic method. Now, how we solve this semi-analytic method? Let us see this. Now, here if you solve this, actually that we are getting the velocity in the next time step based on the force. Now, if you look at here, the force is this P and T is nothing but the generalized force, which is the combination of the radiation force, diffraction force, and sometimes is the combination of the radiation, diffraction as well as the hydrostatics, depending on how you are actually writing the external force. Okay. Now, in this particular case, we are only taking the exciting force and the radiation force. Okay. So, now this P and tau is nothing but the total generalized force, right, and then omega n is the frequency, and then A is the sectional area and rho is the density, right, density of the structure. Okay. So, now how I solve this 2.17? In 2.17, we are writing this sin omega n tau is omega n t minus omega n tau, and then I just write into the sin and cos term, right. So, now here you can see in 2.7 this q n t plus delta t actually having two component. Now, here if you see that this integration is about the tau, this integration is not about the t. So, therefore, actually this equation 2.17 actually we can write in terms of two integral component. One is driven by sin omega n t and another is driven by the cos omega n t, and also it is not that difficult to find out, right, because you see here nothing, like you just write this cos a minus b cos a cos sin a cos b minus sin b cos a, and then you can see here it is the cos omega n tau term is there, which is actually involved the integration, but this sin omega n t is independent of the tau, and similarly in this expression also you can see this should be involved into the integration, but this is actually outside the integration term. So, therefore, and also you can, if you write the rho a equal to m, so therefore, q this equation 2.18, which is q n t plus delta t, actually you can write in terms of two integral, one is multiplied by the sin omega t minus another one is multiplied by the cos omega t. Now our major job, how I could do this integration 2.19 and 2.19a and 2.19b. Right. Now here also, now see that what is p n tau? P n tau is nothing but your the force term that you are getting from 0 to the previous time step. Now if I draw this a graph, and let us say now I am trying to calculate, let us say t is equal to, I mean some 100 second, let us say, okay, and let us take your delta t equal to, let us say 1 second. So, I have the data from 0 to 100 and then I try to approximate about the q at 100 or 101 second. That is actually I am going to do. So, but I have the data, I have the data till this much, right. Now, therefore, I can draw this graph, right, and therefore, actually this integration I can again think of always, as I said, that the best way to deal with the assume everything to be linear or straight line. So, then I just split the whole thing in small the time interval, right, and then I can assume that it is a straight line, the force term is a behave like a straight line in between the time interval. So, the moment I do that, I can write the general force as a in this fashion, right. Whether this you can see is a slope, and I can make it as a delta S I. Right. Now, you see, like the idea is that things are fairly complicated. However, we are using some kind of approximation, some kind of what is say that ignoring some crucial, ignoring some non crucial thing, and then so that I can approximate the solution is little bit simpler way, so that I can get some values or some realistic values, right. So, here what I did, we assume that, now what is the assumptions? The assumption is that again over the time interval, it is the force is not abruptly changing with time. Now, if force does not abruptly changing with time, so therefore, definitely this curve I can approximate as a sum of the straight line. So, therefore, at any interval I can write this equation 2.21, right. Now you see that remaining part is now how to do this, right, because we have done it before also, right. So, here what I do is, suppose I assume there is a NT number of the n tau number of segment. So, therefore, I can sum of each segment, right, and then I substitute this PT for each segment, I multiply with the cos omega n tau, and then I can do the analytic solution, right. So, that is what we do for in case of when you discuss the rigid body solution for IRF based method. That time also we use the same technology, here also we are using the same technology. Now, once you use it, then actually this is the equation 2.22a and equation 2.22b, you are going to get this expression. So, now see why I am not doing it here right now, simply because this has been done for many times, right, before also in initial each and everything that actually we have discussed, and we know that how to do this. So, you should be able to get this expression 2.22 and 2.22b if you follow the previous classes. Now, however, one way is to the brute force way, as I said, like you can take this integration I1 equal to summation I equal to 1 to n tau, right, and then it should be that some I dash I, right, and this I dash I is nothing but that integration from this interval I to I plus 1, and then you write this expression, this we can write as pi tau, and then multiplied by the cos of omega n tau into d tau. So, this is one way, it is called the brute force way to do that, right. And then each time you define this as a straight line, and then you know that how to split up into the uh, the constant term and the linear term, right, and then how we can find out the expression for II. So, we know this part. Now, the same thing actually we can do that a little bit more sophisticated way also. It is, we suppose here what we do is this, we do this is the integration by parts. Now, and then we are taking this P and T as a the first function, and this is a second function. So, as a rule it is P and T, and then you integrate this one, and then minus again 0 to 2, we differentiate the first term and then integrate the second term. This is what we do. Now, if you do this, now you can see that here you can get this differentiation delta P and T by delta T, which is nothing but my dSi, and multiply cos omega n tau is sin omega n tau. So, 1 by omega n is coming here. Now, here also I am writing 0 to tau. Now, if you see here, when I do that for 0 to t, so since sin 0 equal to 0, so we are only having the final term. So, that means we are integrating from 0 to t. If I do that, since the sin 0 equal to 0, so we are only having the final term, right. And then if you integrate, and again if you do this integration, right. So, now here also you have to do this integration. So, again this omega n square is coming, and then this much you have to do 0 to t. So, this is the fundamental idea of the integration by parts, right. Now, the fun is that now if you now discretize it in n-t number of segment, now if you discretize the n-tau number of segment, now this is actually you can get from the second term, because you have to do this integration into the each segment. However, you can see the first term is basically the last term. Why? Because when you do this integration from 0 to t, now when you do this integration from 0 to t, then sin 0 is always equal to 0. So, always we are getting the final term. Now, that can be verified very easily, right. If you make a segment, let us say 0 to, let us say t1, and then again another segment t1 to t2. So, if you do that, and you can see that because this part is 0, and then this part and this part is cancelled out. So, that means what I try to say is that suppose you have 0 comma some delta t, and then you have delta t into delta t plus delta t, I mean 2 delta t, and in so on, and then it is n minus 1 into delta t, and then you have n into delta t. You have this number of segment. Now, since this part equal to 0, now the second integral, because this is coming in the second integral, and in the next time step it is a first integral. So, these two will cancelled out. Similarly, 2 delta t here and 2 delta t here will cancelled out. So, all these things will cancelled out. So, here also n minus 1 into delta t will cancelled out with the next n minus 1 in delta t, and only we are living with this n delta t, right. So, this way also we can arrive the same equation. Okay. So, now we understand how to find out the value of I1. Similar way you can find the value of I2 also. So, then once we know that value of I1 and we know the value of I2, so we can get the total displacement in this equation, which is I1 sin omega n t minus I t into cos omega n t. Now, if you differentiate with respect to t, and remember I am differentiating with respect to t. So, therefore, I1 and I2 it does not affect. So, therefore, it is only sufficient to differentiate this sin omega t, which is nothing but the cos omega t, and if you differentiate the cos omega t, you will get the value for the sin omega t, right. And so, this is how I can get the solution for Qn and solution for Q dash n. Now, once we know the solution for Qn, I know the solution for Qn dash. So, I know the entire solution at time step t plus delta t, right. So, now in the next level we use this Qn t again to figure out my that f of x t, the total external force, which is combination of this plus combination of the radiation force. So, when you calculate the combination radiation force, so that time again you have to use the value for Qn dash t, right. So, now this is how actually you can do the fluid structure coupling, and you can get the solution for the deflection, and then you can calculate the shear force, the bending moment, everything using the semi analytic method. Now, let us see that some results on this semi analytic method, and let us see that how good this result is with comparison to the finite element bound element coupling method. Okay. Now, if you see that this is the results for the different modes that we are getting it using the modal superposition method, and then you see that here we are comparing the impulse response function, which is matching very nicely. So, now this is the result of the non-dimensional shear force and bend and I think the second one is the bending moment, and you can see that this it is absolutely matching very well with the public results, and this Kara actually using the that he used the time domain solution. However, the structural solution is similar. He used the structural solution using the modal superposition. That is how he solved the structural problem. However, he used the time domain panel method to calculate the radiation force, diffraction force, etc. Okay. But now you can see that even if we see we are telling that this is a simplistic method or maybe a semi analytic method, but the results are matching very well. And also you can see that the results are very stable, and also you can see that is how we can get the shear force and the bending moment, right. This is the shear force and bending moment dynamic when actually I can have the maximum bending moment at the midship. So, at that time we are calculating the shear force, and when the wavelength is equals to the ship length. Okay. So, now and also we are just showing that how the flexibility actually plays a significant role. If we change the flexibility, you can see that when it is more flexible, then you can have the less shear force and bending. Of course, it is possible when it is it is more flexible, definitely the it absorbs the more energy. So, therefore, the deflection or the bending it should be less, right. Now, here that is the interesting result that this is the IRF stands for this semi analytic method, and then the TD it stands for the time domain method that we discussed in the previous class. And you can see that TD is much sophisticated method compared to this one, but however, when you see the result S equal to 10 to the minus 2, it implies more or less the structure is made of steel, uh, is a dimensionless quantity. Now, idea is that we can see that though we are saying this IRF is bit simplistic method, but quality wise the results are as good as the sophisticated so called sophisticated uh, panel method, I mean that FEM BM based panel method, right. So, that is the idea, like, so this is the major advantage of this particular method. Only thing that we required is the beforehand we have to have the added mass and damping of the frequency domain data code, uh, the frequency domain added mass, frequency domain damping, frequency domain exciting force for flexible structures. This is the only thing that we required. Uh, we can say that is the only disadvantage of this particular code. But if it is available to you and if it is given in some literature, so definitely this is a very powerful tool to capture the flexibility of a large floating structure. Okay. Again, you can see that all the results are matches quite well. So, definitely we can see that these results are really good using the semi analytic method. Now, this is the references that we like to use, that, and then I would recommend you to see this paper, and in this paper actually you can see that all these frequency band data are available, right. And also this paper you can get lot of results. uh, these two actually all are very important paper. These two actually it is very useful for our particular this course. Okay. So, with this we stop this semi analytic method, and from the next class we are going to start that discuss the basic thing about the slamming, and then uh, green water, and then how we can use this slamming green water, I mean the impact of slamming and green water into this semi-analytic code as well as the time domain method code. Those things we are going to discuss from the next class. Thank you.